Hey there, welcome to this explainer. Let's just jump right into a really fascinating historical puzzle. Picture this. You're one of the greatest economic minds of the 20th century, right? And suddenly, you're hit with a seemingly impossible challenge by a prominent physicist. Well, that's exactly what went down in 1969 for the legendary economist Paul Samuelson.
Okay, let's dive into this. So the physicist basically asked Samuelson to name just one, literally a single law in economics that is both completely true and non-trivial. Samuelson's famous response? He said, the law of comparative advantage. And look, that's a brilliant economic concept for sure, but it's qualitative, you know? Physicists, well, they want cold, hard math. They wanted a perfectly reliable, quantitative law.
So it begs the question, right? Is there actually a true, non-trivial mathematical law in economics? For decades, honestly, it seemed pretty unlikely. But today, we finally have an answer. Turns out, there's this hidden mathematical skeleton key that unlocks the structural secrets of, well, not just money and markets, but the entire world around us.
Part 1. The Quest for Economic Laws. Economics has historically struggled to pin down reliable quantitative laws. Mostly because, let's face it, we humans rarely act like perfectly rational robots. And this brilliantly illustrates the big breakthrough we're uncovering today. The modern answer to that physicist challenge? It's power laws. These are rigid, inescapable mathematical patterns that are just hiding in plain sight across the entire global economy.
Moving on to Section 2, Discovering the Hidden Pattern. We're going to see exactly what this mysterious pattern is and where it pops up in our everyday lives.
So here's the basic definition of a power law, which you might also hear called a scaling law. It's a relationship where y equals a constant times x to the power of beta. Okay, I know, don't let the algebra intimidate you. Simply put, we're really just looking at how things scale when they grow. If your variable x multiplies by 10, y is going to scale by a highly predictable exact mathematical exponent.
And the empirical facts here? Absolutely mind-bending. Check out these examples. City sizes in the U.S. with over 250,000 people. Their rank is perfectly proportional to the inverse of their size. That's known as Zipf's law. Or what about firm sizes? The number of companies scales strictly with an exponent of 1.059 based on employee count. And the stock market, get this. Daily fluctuations follow a rigid cubic law with an exponent of 3. Cities, companies, stocks. Totally unrelated phenomena, right? Yet they bizarrely obey the exact same structural rules. It's wild.
Now, what's really interesting about this slide is the stark contrast between how we think the world works and how it actually works. Normal bell curve thinking, a Gaussian distribution, treats the world like a series of independent coin flips. Under a bell curve, an extreme anomaly, what statisticians call a 10 sigma event, is 10 to the power of 22 times less likely than a normal event. It's practically impossible. But in a power law distribution, extreme events are frequent. In a market of 1,000 stocks, a massive market fluctuation happens almost every single day. We don't live in a neat bell curve world. We're living in a messy, fat-tailed world.
Section 3. What causes power laws? So, how exactly do these identical mathematical patterns emerge in totally unrelated fields?
What's the mechanical engine driving all of this? Well, it essentially boils down to proportional random growth, which is often called Jabot's law. Walk through this mechanical process with me real quick. First, you start with an initial distribution of things, say cities or firms. Second, they grow and shrink randomly, but proportionally. Third, you introduce a tiny friction, like a minimum fixed cost just to keep a firm alive, or a lower bound on size. And fourth, the system mechanically reaches a steady state. So, constant returns to scale plus a little bit of randomness magically yields a perfect power law.
And here's the kicker. When that friction is extremely tiny and the total population you're allocating is finite, the exponent mechanically has to become exactly 1. It literally can't be lower, or the average size would mathematically be infinite. This single elegant mechanism completely explains that famous Zipf's law we talked about, governing why New York, Los Angeles, and Chicago are exactly the comparative sizes that they are.
Part 4. The Economics of Superstars. Let's apply this concept directly to a really hot-button issue. Why top CEOs, star athletes, and famous artists get paid absolutely astronomical sums of money.
The answer actually lies in this specific number, 1/3. Researchers have found a rigid scaling exponent that links CEO pay directly to firm size. It's an empirical relationship, known as Robert's Law. Basically, if a firm becomes 8 times bigger than the median firm, the CEO makes exactly twice as much. Why? Because 8 to the power of 1/3 is 2. The pay scales exactly with the size of the firm to the 1/3 power.
So, the crucial point is what economists call extreme value theory. When massive multi-billion-dollar firms compete to hire the absolute best talent out there, microscopic differences in a CEO's skill end up resulting in unboundedly huge differences in pay. Skyrocketing executive pay isn't necessarily just random corporate greed. Fundamentally, it's a mechanical matching process. The market is just matching the very highest tier of talent to vastly scaling firms.
Section 5, the granular economy. This is where we transition to the macro level because understanding power laws is absolutely crucial for wrapping our heads around national and global economic crashes.
We often tend to think of the economy as this smooth continuum of millions of tiny businesses, right? Where one failing is perfectly offset by another one succeeding. But that is a total illusion. Because of power laws, the economy is actually made of incompressible, massive grains. A few big firms are so unbelievably massive that they warp the gravity of the whole system. They simply do not cancel each other out.
Just look at this shocking statistic for South Korea's GDP. Samsung alone, just one company, accounts for 14% of the entire country's gross domestic product. The next top 9 groups account for another 40%. The rest of the millions of businesses in the entire country make up the remaining 46%. To put that into perspective, a minor hiccup in just one company, Samsung, can literally tank an entire nation's GDP. No way around it.
Let's move to and see how this builds into our broader understanding of recessions, because it's fascinating. Idiosyncratic shocks, which just means sudden, isolated problems affecting a single firm, explain about 1/3 of all U.S. GDP fluctuations. In France, firm-level shocks explain over 50%. Even the famous Great Moderation, that period of seemingly low economic volatility in the U.S., was largely just a structural shift away from a few concentrated heavy manufacturing sectors. So national recessions often don't start with abstract systemic issues. They start with just a few massively scaled corporations stumbling. But here is where this explainer gets truly profound. Power laws actually reveal the absolute essence of a complex system, even completely outside of economics. This secret code governs the natural world just as strictly as it governs money and markets.
Take a look at this fraction, 3/4. Over in biology, there's something called Kleiber's Law. An animal's metabolic energy requirement scales precisely at its mass to the 3/4 power. Whether you're looking at a tiny little mouse, a dog, or a giant elephant, the math holds perfectly. It completely ignores almost all other biological details like fur thickness, predator status, or climate. It's like an optimal network designed by nature to distribute nutrients, behaving exactly like an optimal economic network distributing capital.
Which brings us to a final, pretty profound question to consider. Are we just living through a chaotic series of random events? Or are our cities, our stock markets, and even our own biological bodies actually highly optimized networks governed by invisible, unbreakable mathematical rules? Once you see the power law, you really start seeing the hidden architecture of your entire everyday life. Thank you so much for exploring this with me today, and keep looking for those patterns.